Six Sigma Analyze Phase. Hypothesis Testing Concepts. Welcome to this session on hypothesis testing, a foundational statistical tool in Six Sigma. In any Six Sigma project, we aim to make data-driven decisions. Hypothesis testing helps us do just that. By allowing us to test assumptions and validate whether observed changes in a process are statistically significant or merely due to random chance. In this presentation, we'll cover the basics of hypothesis testing, what null and alternative hypotheses mean, the concept of Type 1 and Type 2 errors, significance levels, commonly referred to as alpha, and the interpretation of p-values. These concepts are not just theoretical. They're essential tools for improving process performance. Whether you're trying to reduce defects, improve efficiency, or validate a new solution, hypothesis testing ensures that your conclusions are backed by solid statistical evidence. Think of this as the backbone of analysis in the analyze and improve phases of DMX. Understanding and applying these principles correctly will increase your confidence in the results and enable smarter decisions that are defensible and repeatable. Key to success in Six Sigma. Let's dive deeper and understand how hypothesis testing works and why it matters. This slide presents the agenda for today's session. We will walk through the core components of hypothesis testing that are crucial for effective Six Sigma analysis and decision-making. Let's quickly go through each agenda item. 1. Hypothesis testing. Concept. We'll start with the basics. What hypothesis testing is, why it's used in Six Sigma, and how it supports data-driven decision-making. Second, null and alternate hypothesis. We'll define these foundational terms. The null hypothesis generally represents the status quo, while the alternate hypothesis reflects the change we're trying to validate through data. 3. Concept of p-value. Next, we'll discuss the p-value, a key output of hypothesis testing. Understanding what a p-value indicates will help you decide whether to reject or fail to reject the null hypothesis. 4. Confidence level. We'll explore the confidence level, which indicates how certain we are about our results. This directly relates to the risk of making an incorrect decision during testing. 5. Truth table. This table helps visualize the possible outcomes of hypothesis testing, such as true positives, false positives, type 1 error, false negatives, type 2 error, and true negatives. 6. Understanding sample and population. Finally, we'll touch on the importance of selecting a representative sample from a larger population and how this impacts the reliability of our test results. By the end of this session, you should have a clear understanding of how each of these elements contributes to making statistically sound decisions in your Six Sigma projects. Let's begin with the first topic, the core concept of hypothesis testing. 1. A hypothesis is essentially an assumption or claim. In our process improvement efforts, we often make assumptions about the factors that influence performance. Hypothesis testing is the method we use to validate these assumptions using data. 2. Hypothesis testing is binary in structure, meaning we always test two competing claims. The null hypothesis, H0, assumes that there is no effect, no difference, or no impact, essentially the status quo. The alternate hypothesis, H1 or AA, assumes there is an effect, a difference, or a change. Something has happened. 3. The goal of hypothesis testing is to determine whether we have enough statistical evidence to reject the null hypothesis in favor of the alternate. If we fail to prove the alternate, we retain the null. But this doesn't mean the null is true. It just means we didn't find enough evidence against it. 4. Why do we do this in Six Sigma? Because we want to ensure that any improvements we observe are not due to random chance. We want to confirm if our potential XS, causal factors, are truly affecting our Y, output. And, most importantly, we want to make data-driven decisions when moving from sample analysis to full-scale implementation. Now, let's also look at the 3 supporting points shown at the bottom of the slide. First, hypothesis testing helps us validate whether the factors we've identified actually influence the project output. It gives credibility to our findings. Second, because we often work with samples, not entire populations, hypothesis testing allows us to make statistically sound inferences about the population based on sample data. Third, the type of hypothesis test we use will vary based on the type of data we're analyzing, whether it's continuous, discrete, categorical, etc. Understanding this foundation is critical as it sets the stage for all subsequent tests and analyses we'll perform in our Six Sigma project. Now, let's delve deeper into the concept of the null hypothesis, which is denoted as H0. The null hypothesis, H0, represents the assumption that there is no effect, no difference, or no relationship. It reflects the status quo or baseline condition. The alternate hypothesis, HA, on the other hand, is the claim that there is an effect or impact, the claim we're trying to prove with evidence. Remember, we never directly prove the null hypothesis. Instead, we test whether there's enough evidence to reject it in favor of the alternate. Let's understand this with a few examples listed on the slide. 1. If H0 says X does not significantly impact Y, then HA will say X significantly impacts Y. 2. If H0 says data is normal, then HA says data is not normal. 3. If H0 says data is random, then HA claims data is not random. These opposing pairs help us define the direction of the hypothesis test. Let's look at the bottom portion of the slide, which provides scenarios. When testing relationships between variables, HA claims that X significantly affects Y. During a randomness study, HA claims that the data is not random, challenging the null. In a normality study, HA claims that the data is not normally distributed. In summary, the null hypothesis always assumes no change or no effect. The alternate hypothesis is what we hope to prove with evidence. The goal of hypothesis testing is to challenge the null, and only if we find sufficient statistical evidence do we reject it. This logic of opposition between H0 and high forms the foundation for every test we'll perform later. Let's now understand the alternate hypothesis, represented as HA. The alternate hypothesis is the claim we are attempting to prove, that something significant is happening in the data. It's the opposite of the null hypothesis, which assumes there's no change or no effect. Let's walk through the 3 default assumptions we make about data, and how the alternate hypothesis challenges each of them. 1. By default, we assume that one variable does not impact another. Unless we have statistical evidence to say otherwise, we consider the factors, XS, and outcomes, YS, to be unrelated. HA challenges this by claiming factor X significantly impacts response Y. 2. We assume data is random, that is, the data doesn't follow any specific pattern. No clusters, no trends, no oscillations. HA contradicts this, saying data is not random, meaning there may be special cause patterns or signals in the data. 3. We assume data follows a normal distribution. This is a key assumption in many statistical models and tests. HA says, data is not normally distributed, meaning it deviates from the expected bell curve. At the bottom of the slide, you'll see these summarized in 3 visual blocks. When checking relationships, HA says X impacts Y. In randomness studies, HA says the data is not random. In normality checks, HA says the data is not normal. So, whenever we conduct a hypothesis test, we're essentially collecting evidence to support the alternate hypothesis. If the evidence is strong enough, we reject the null and accept HA. This is how we move from assumptions to validated insights using data in Six Sigma. Let's talk about one of the most important metrics in hypothesis testing: the p-value. What is a p-value? The p-value is the decision criteria we use to accept or reject the alternate hypothesis, HA. It is also referred to as the value of significance and represents a probability ranging between 0 and 1. A lower p-value suggests that the observed results are less likely due to chance and more likely due to an actual effect. Let's simplify. If p-value is low, typically less than 0.05, we say the result is statistically significant, and we reject the null hypothesis in favor of the alternate. If p-value is high, it means the observed result could very well be due to random chance, and we fail to reject the null hypothesis. Now look at the two supporting blocks below. 1. Higher the contribution of chance, lower the impact of X on Y. This means if your p-value is high, most of the variation in your response, Y, can be attributed to randomness, not the factor, X, you're testing. So, high chance equals weak evidence equals low confidence in X impacting Y. 2. Chance depicts random variation. In order to prove the alternate hypothesis, HA, we must demonstrate that the variation we're seeing is not due to chance, but rather due to the effect of the factor, X. That's why a low p-value gives us confidence to say, yes, this factor matters. Important takeaway: the p-value doesn't prove anything. It only tells us how likely it is that the observed results happened by chance. The smaller that likelihood, the more confident we are in rejecting the null hypothesis. In Six Sigma, using the p-value correctly ensures that our process improvements are statistically justified, not based on assumptions. Let's continue our discussion on the p-value, with a focus on how to interpret it during hypothesis testing. As mentioned before, the p-value is the probability that the observed result is due to chance, nothing more. This slide explains what we do with that p-value once we calculate it. Here's the rule of thumb used in Six Sigma and general statistics. If p-value is less than alpha, commonly 0.05, we reject the null hypothesis, H, and accept the alternate hypothesis, HA. This means the result is statistically significant and not likely due to chance. If p-value is greater than or equal to alpha, we fail to reject the null hypothesis. This means the observed result may just be due to chance, and we don't have enough evidence to accept HA. Important point: the alpha value, typically 0.05, is pre-decided and represents our tolerance for error. It's also called the level of significance. Now let's look at the three support boxes at the bottom. 1. Alpha and confidence level. Alpha is the threshold value, commonly 0.05, and is the inverse of the confidence level. So, if we use a 95% confidence level, our alpha equals 1 minus 0.95 equals 0.05. 2. Why 0.05? It's a convention used in most hypothesis tests. It implies we're okay with a 5% risk of wrongly rejecting the null hypothesis. 3. More confidence equals more data. If you want higher confidence in your results, say 99%, you'll need more data to reduce uncertainty and maintain statistical power. So, to summarize, p less than 0.05, strong evidence against the null, except AHA. p greater than or equal to 0.05. Insufficient evidence, retain H. This logic is the cornerstone of all decision-making in hypothesis testing, and absolutely essential in Six Sigma analysis. Let's now look at how to apply the p-value logic using a couple of simple, real-world examples. As we've discussed earlier, the p-value tells us the probability that our observed relationship is due to random chance. Example 1. Salary and attrition. Suppose we're testing whether salary impacts employee attrition. The hypothesis test gives us a p-value of 0.09. This means that 9% of the result could be due to chance, and 91% is attributed to the salary factor. Since 0.09 is greater than 0.05, we fail to reject the null hypothesis. We do not have enough confidence to accept the alternate hypothesis that salary impacts attrition. Example 2. NPS and income. We now test whether Net Promoter Score, NPS, is dependent on respondent income. The p-value from the test is 0.12, meaning that 12% of the variation could be random and 88% may be attributed to income. Again, since 0.12 is greater than 0.05, we fail to reject H. We do not have sufficient statistical evidence to accept the alternate hypothesis. Let's now talk about an important foundational concept in hypothesis testing: the relationship between samples and populations. In theory, we want to study the entire population to understand behavior or impact, but in practice, this is often not possible. And here's why. Studying the full population can be too time-consuming. It may be too costly. The population might be unavailable or inaccessible. And sometimes we don't even know who exactly constitutes the full population. Because of these practical constraints, we use a sample, a small representative group, to study and infer what's happening in the population. But here's the key point. We must choose the sample carefully and without bias. Otherwise, the conclusions we draw will be flawed and may not reflect the true population behavior. This is where hypothesis testing becomes essential. It allows us to validate whether patterns in the sample reflect those in the population, use statistical tools to measure confidence in our conclusions, make informed decisions without having to test the entire population. As stated at the bottom of the slide, you use hypothesis tests because you are studying a sample, and you want to draw inference about the population. So in any Six Sigma project, remember, you'll almost always be working with sample data, and hypothesis testing is the tool that bridges the gap between your sample insights and population-wide conclusions. One of the most crucial concepts in hypothesis testing is the confidence level, often abbreviated as CL. Let's start with a simple definition. The confidence level is the degree of certainty or surety we have that the decision we are making about the population, based on sample data, is correct. It tells us how confident we are that we're not making a mistake, specifically a type 1 error, which is rejecting the null hypothesis when it's actually true. In layman terms, confidence level is the trust we place in our test results. It's how sure we are that our findings from the sample apply to the population. Mathematically, confidence level equals 1 minus alpha. If your alpha is 0.05, which is common, then confidence level equals 1 minus 0.05 equals 0.95 or 95%. This means we're 95% confident in our decision, and we accept a 5% risk of making an error. Important insights at the bottom of the slide. 1. Confidence level is directly proportional to sample size. Bigger sample equals better representation of the population, equals higher confidence, 2. CL equals 1-alpha level. O, as explained, the lower your alpha, the higher your confidence level. 3. More confidence needs more data. If you want 99% confidence instead of 95%, you'll need a larger sample to maintain statistical power. In summary, confidence level reflects our statistical certainty. It's a key parameter in setting thresholds for hypothesis tests, and it's deeply tied to both sample size and risk tolerance, alpha. This concept helps us interpret test results responsibly, especially when the goal is to make decisions that scale from sample to population. In this slide, we focus on alpha risk, which is also known as a type 1 error. Let's start with a simple definition. Alpha risk is the risk of rejecting the null hypothesis, H, when it is actually true. That means we are detecting an effect or difference that doesn't actually exist. A false positive. Think of it like making a wrong call in your statistical test. Let's break it down. It's expressed as a probability, typically 0.05 or 5%. This means there's a 5% chance you're making a type 1 error when using a standard alpha. This value isn't fixed. It's set based on the risk tolerance for the decision being made. Typical alpha values: less than 1% for high-stakes decisions, example in safety-critical systems. 5% is the most common. Up to 10% for low-risk or exploratory studies. Link with confidence level. Confidence level equals 1 minus alpha. So, if alpha is 5%, the confidence level is 95%. This is the degree of surety you have in avoiding a type 1 error. Analogy. The slide gives a courtroom analogy, declaring someone guilty when they are actually innocent. This is exactly like rejecting H when it's actually true. It's a false alarm. Acting on something that's not really there. In Six Sigma and any data-driven decision-making, always be aware of your alpha risk. Set it appropriately based on how costly a wrong decision might be. And remember, reducing alpha increases your confidence, but may require more data. Now that we've covered alpha risk, let's explore the second common type of error in hypothesis testing. Beta risk, also known as a type 2 error. What is beta risk? Beta risk is the probability of failing to reject the null hypothesis, H, when it is actually false. In other words, missing a real effect or change that truly exists. It's the opposite of a type 1 error. Instead of a false positive, it's a false negative. Example, as shown at the bottom, imagine a courtroom analogy again. Concluding someone is not guilty, failing to reject H when they are actually guilty. H1 is true. So, with beta risk, we miss something that matters. We assume no effect when there actually is one. Beta risk characteristics, expressed as a probability, usually around 0.1 or 10%. It is influenced by 1. The size of the true difference, smaller effects are harder to detect. 2. Sample size, larger samples reduce beta risk and improve accuracy. 3. Practical norms. A 10% beta risk is generally considered acceptable in many studies. The concept of statistical power. This is where an important formula comes in. Power of a test equals 1 minus beta risk. This means the power of a test tells us the probability of correctly detecting a real effect. So, if your beta is 10%, your test power is 90%, meaning there's a 90% chance your test will successfully detect the actual effect when it exists. Summary. Alpha risk, Dusser's false positive. You see an effect that doesn't exist. Beta risk, Dusser false negative. You miss an effect that does exist. Both are important, but beta risk is particularly critical in situations where missing a real signal can have serious consequences. For example, in healthcare trials or quality control scenarios. By increasing sample size or selecting a more sensitive test, we can reduce beta risk and increase our test's reliability. Let's now understand what a confidence interval, or CI, means in hypothesis testing and data analysis. A confidence interval is a range of values, calculated from sample data, that is likely to contain the true value for the population. For example, if we say a result has a 95% confidence interval, we mean that we are 95% confident that the true population parameter lies within this range. Key concepts from the slide. Checkmark CI shows the reliability of an estimate, but not absolute certainty. It gives us a likely range, not a guarantee. A 95% confidence interval means we may still be wrong 5% of the time. That's the alpha error. Larger sample sizes give us narrower, more precise CIs. Smaller samples equals wider range. Different samples will yield different confidence intervals because each sample is just one possible view of the population. CI does not equal proof. It gives us a statistical likelihood, not a conclusion. Examples at the bottom. 1. Survey support. If a survey shows 60% plus or minus 5% support with 95% confidence interval, then we say the true support lies between 55% and 65%. 2.8 to 3.2 years at 95% confidence interval means the true average lifespan likely lies within that range. Third, defect rate. A machine has a 2% defect rate plus or minus 1% at 99% confidence interval, meaning the true rate is likely between 1% and 3%. Summary. CI is a way of expressing the uncertainty around your sample estimates. The narrower the CI, the more reliable the estimate. The higher the confidence level, the wider the interval usually becomes, unless sample size is large. CI is a critical concept in Lean Six Sigma for decision-making, performance evaluation, and risk estimation. Let's close our session with a quick summary of the key concepts in hypothesis testing, visualized in this step-down funnel format. Two hypotheses, null, H, and alternate, HA, are always tested. Any hypothesis test starts with defining these two competing statements. The alternate hypothesis, HA, is what we test. We attempt to prove HA using data. If we fail to prove HA, we assume that H stands. This does not mean H is true, just that we didn't have enough evidence to reject it. We base our decision on the p-value. The p-value is the central statistic that tells us whether our sample evidence is strong enough to reject H. If p-value greater than or equal to alpha, then we do not reject H. There's not enough evidence to support high. We assume the observed result might just be due to chance. If p-value less than alpha, we reject H and accept HA. This means the observed result is unlikely due to chance. We consider it statistically significant. Final wrap-up. Hypothesis testing is about evidence-based decision-making. It relies on probabilities, not certainties. The logic flows from defining hypotheses, setting alpha, calculating p-value, drawing a conclusion. This logical sequence is used in virtually every statistical test across Six Sigma, quality control, research, and analytics. This second summary slide reinforces some of the more technical relationships and definitions behind hypothesis testing. Let's walk through each layer. Top. Confidence level is dependent on sample size. The larger the sample size, the more accurately it represents the population. This means you can be more confident in your results, i.e., the confidence level increases with sample size. Next, confidence level equals 1 minus alpha. This is the mathematical definition of confidence level. For example, if alpha is 0.055%, then your confidence level is 95%. It reflects your certainty in not making a type 1 error. Alpha error, type 1 error. This is the mistake of rejecting the null hypothesis, H, when it is actually true. In other words, you accept the alternate hypothesis, HA, incorrectly. Beta error, type 2 error. This is the opposite mistake, failing to reject H when it is false. In this case, you miss detecting the actual impact. You accept H when hey is actually true. Bottom. Power equals 1 minus beta. The power of a test is your ability to detect a true effect when it exists. Higher power means lower risk of a type 2 error. A good hypothesis test should aim for power greater than or equal to 80%, meaning beta less than or equal to 0.20. Let's wrap up this session with the key takeaways. A quick checklist of what you should now understand and be able to apply regarding hypothesis testing. First point, hypothesis testing helps us decide whether results are due to real effects or just random chance. This is the core of data-driven decision-making, making conclusions that are statistically valid. Second point, we work with two hypotheses. Null hypothesis, H0, assumes no effect, no change, or no difference. Alternate hypothesis, H1 or Chi, assumes there is a significant effect. Third point, we use the p-value to make decisions. If p is less than 0.05, we reject the null and accept ha. The effect is statistically significant. If p is greater than or equal to 0.05, we fail to reject H0, meaning there isn't enough evidence to support HA. Fourth point, alpha. Alpha is the threshold or risk level we're willing to tolerate, usually set at 0.05 or 5%. It defines how confident we want to be and how much risk of a type 1 error we're willing to accept. Fifth point, hypothesis tests are performed on samples, not the entire population. The goal is to infer what's likely true for the whole population based on the sample analysis. Sixth point, larger samples equal more reliable results. With a bigger sample, your estimates are more stable and your confidence intervals become narrower. Encourage the participants to revisit these concepts whenever they plan or interpret statistical analysis in real-world projects, especially in Six Sigma, quality improvement, or research settings.